Hi everybody. Today my topics is limits. The notion of a limit is fundamental to the study of calculus. That's why we need to know the meaning of the limit of a function. Actually, the important concept of a limit is the limit of function of x equals L as x approaches a. When studying a function, say y equal to function of x, we are interested in the function's behavior near a particular points, but not exactly at that point. From this graph, it is clear that the use of limits in dealing with functions requires an understanding of the projected behavior of the functions near a certain points a, not the behavior exactly at point a. Here we are analyzing a limit by graphical approach. To analyze a limit, I shall go ahead first drawing a graph of a line. We can see it here. And its equation is y equal to function of x equal to x plus 2. Here, domain is x equal to 2. Here our task is to discuss the behavior of the values of function of x when x is close to 2. The vertical line in this graph, we can see it here, it represents the values of x that are close to 2. So the corresponding horizontal lines, all these, identify the value of function of x associated with each value of x. So the value of x get closer and closer to 2 on either side of 2. The corresponding value of fx get closer and closer to 4. Symbolically, we can write like this one, and it is the limit of function of x as x approaches to, it is equal to 4. Also to be noted here that functions of 2 equal to 4. So the value of the function at x equal to, x at value of the function x, what I can tell, the value of the function at 2, because here already I put 2. The limit of function as x approaches to. I repeat the things again. The value of the function at 2 and the limit of function as x approaches to are the same. It is 4. Most important points. Finding a limit using tables. That's what we will do it here. For this part, x approaches 2 from the left and x values are from 1 to 1.999 and then 2. And as well, x approaches 2 from the right and the value of x are from 3 to 2.001 and then 2. Here the limit of function of x as x approaches 2 is 4. On the graph we can see it here, as well on the table we have to assume that this will be 4. So what does it mean? It means in upward directions value of fx approaches from 3 to 3.999 and then 4. And as well in the downward directions fx value approaches from 5 to 4.001 and then 4. That's what we got the clear picture from the graph as well as from the table. There are two classic problems in calculus. One is tangent line problem, which creates differential calculus, and other is the area problem, which creates integral calculus. These two gives us idea of the way limits are used in calculus. Here my discussion is about tangent line problem. To obtain a definition of a tangent line that applies to the curve, we can see it here. This is tangent, this is the curve. So to obtain the definition of a tangent line that applies to the curve, we must view these tangent lines in more specific way. That's why let's look at this problem of trying to find a tangent line to parabola. How to do that? For this purpose, suppose we are interested in the tangent line at point R on this curve on xy plane, and S is at any point, S is any point that also lies on this curve, and of course this point is different from this point R. Now the line through R and S is called the secant line for the curve at R. Now if we move the point S, this one, along the curve, you see this point, S point, this second point is here, third point is here, fourth point is here, so it is moving along the curve. Now if we move the point S along the curve towards where R, then the secant line, it will rotate towards limiting positions rotate in this direction towards a limiting positions. This is the limiting position line. The line in this limiting positions is what we will consider to be the tangent line at R. We can see it here very clearly. As well as S approaches R along parabola, the corresponding secant line rotates about R and approaches the tangent line. So when such a limiting position exists, what we can see it here, the slope of tangent line is said to be the limit of slopes of secant lines. It is a most important point, this line. The slope of the tangent line is said to be the limit of the slopes of the secant lines. This is most important line. As we let S move along the parabola and getting closer and closer to R, then the limiting position of the secant line through R and S will coincide with that of the tangent line at R. And it in turn suggests that the value of M sec, I mean slope of the secant line, will get closer and closer to the value of slope of tangent line M10 as R moves towards S along the curves. That's why we can conclude that finding the tangent line, here you can see that finding the tangent line at a point R is equivalent to finding the slope of the tangent line at R. This is very important line. Now in the previous slide, we learned that we will be able to find an equation of the tangent line as soon as we know its slope M. That's what we learned in the previous slide. But the difficulty is that we know only one point. Here we can see that. That is R on the tangent line, whereas we need 2 points to compute the slope. So assume x is not equal to 1, and as a result, this is very important point, to get 2 points we assume that x is not equal to 1, and as a result S is not equal to R. Then we can write MRS, I mean slope equal to x square minus 1 divided by x minus 1. Here you can see that x square minus 1, this perpendicular, this is the base, x minus 1. So this is the slope MRS. To get an idea of the behavior of the graph of function of x near x equal to 1, I am telling near x equal to 1, we can use two sets of x values. One set that approaches 1 from the left and another set that approaches 1 from the right. Here, for the points R, what is that point? Its x is 1.1 and x square, I mean value of y, equal to 1.21. So for this point, we have to find this MRS. This one we already got in previous slide. So we are following this, putting the value of x square and x. So we get MRS equal to 1.21, as you can see it here, and other is 1.1. So MRS equal to 2.1. This table shows the value of MRS for several values of x close to 1. Already I told x approaches 1 from the left, x approaches 1 from the right. So according to this, we got the slope MRS for several values of x close to 1. The closer s is to r, the closer x is to 1. It appears from the table. So the closer MRS is to 2. That is important point here. So we can say this behavior indicates that slope of the tangent line should be m equal to 2. Should be m equal to 2. Here I highlight this to show that this 2.4, this 2.1, it is the slope of RS and this is the value of x. Here the slope of the tangent line is the limit of the slopes of the secant lines. It's very important. So limit MRS equal to m as r approaches s. So for any x is not equal to 1, this is very important points. For any x is not equal to 1, we can simplify the formula by factoring the numerator and cancelling the common factors. And what we did here, as a result, we got this value is 2. I am assuming that the slope of the tangent line is indeed, it is 2, m equal to 2. Already we saw it in previous slides. And if I use the point slope form of the equation of the line to write the equation of the tangent line, throw 1, 1, then slope m equal to y minus 1 divided by x minus 1. Then from this formula, m equal to y minus 1 by x minus 1, we get this, putting the value of m as 2. Now with simplifications, we get y equal to 2x minus 1. This is the equation of the tangent line. I highlight this to show that this is the equation of this red line, which is tangent on this curve y equal to x square. That's all for today, and thank you very much for watching this video. Please click on subscribe. this one.